And apparently the space-time proximity of the LHC launch and all these giant machines like the Alice detector, I decided to give very brief review of the situation with the quark-gluon plasma and computations in string theory. So we have to remember one thing, that LHC is not only about proton-proton collisions, but it is also about the heavy ion program, right? The heavy ion collisions. And the outline of the talk, as it stands now, is the talk is divided into two parts. One of them is a very short summary of a subset, particular subset of the gauge gravity duality results for strongly coupled gauge theories at finite temperature and density, which involves thermodynamics, first and second order transport coefficients, and also a relationship between the viscosity entropy ratio and the RHIC elliptic flow. In part two, I will come to low temperature situation in which we consider certain holographic models for quantum liquids. And that will involve specific heat computation at low temperature limit, and also the zero sound mode, which was predicted by Landau for thermal liquids 50 years ago. So, over the last several years, holographic or gauge gravity duality methods were used to study strongly coupled gauge theories at finite temperature and density, and these studies were motivated by the heavy ion collision program at RHIC and LHC, and the necessity to understand hot and dense nuclear matter in the regime of intermediate coupling. Alpha S at the temperatures of RHIC and LHC will not be very small. It will be of order 1 or slightly smaller. As a result of these studies, theoretical studies, we now have a better understanding of thermodynamics and especially kinetics, which means transport properties of strongly coupled gauge theories. Of course, all these calculations are done for theoretical models, such as n equals 4 super Mills and its cousins, including non-conformal theories, theories of fundamental matter, and so on. Numerous cousins, but it is not QCD. We have to remember that. So we don't really know, for example, real functions like A to over S as a function of lambda QCD over temperature for QCD itself. That said, it is still a useful approach. And we know that these heavy ion collisions creates the hot and dense nuclear matter known as the quark-gluon plasma. One had to note qualitative difference between the proton-proton collisions and, for example, gold-gold ion collisions. In the second case, we have a certain number of collective effects which are not present in PP collisions. And any model of string theory or gravity should account for this difference. That is an important thing to remember. Evolution of this plasma fireball is essentially described by relativistic fluid dynamics or relativistic Navier-Stokes equations. And we need to know, in order to solve these equations, we need to know thermodynamics, namely equation of state, and we also need to know kinetics, namely first and second order transport coefficients in the regime of intermediate coupling strength. But it is not the full story. We also need to know something else. And that something else is quite important. We also need to know initial conditions, namely the initial energy density or nuclear profile of the colliding nuclei. And we also need to know things like thermalization time, when we have to start hydroevolution, and the end of hydroevolution, which goes by the name freeze-out conditions. So these extra things turn out to be important when we talk about the attempts to extract, for example, value of viscosity in QCD from RHIC data, experimental data. So the story of thermodynamics is the following. You can consider this plot, this is energy density versus temperature for various gauge theories, normalized by Stefan Boltzmann value epsilon naught as a function of temperature in units of critical temperature. So somewhere far to the left we have ideal gas of hadrons, and then there is a rather sharp crossover, and here somewhere very far to the right we have ideal gas of quarks and gluons. And in between there is this very long plateau of intermediate coupling. And RHIC operates somewhere here, and LHC, this Alice will measure things somewhere over here. So this is not the ideal gas of quarks and gluons, and we have to develop certain methods to look into this region, not only perturbatively from that far right side, but also non-perturbatively. And so the purpose of applying the DSCFT methods, so notice that, okay, so these lattice data here, and notice that in this normalization, our favorite n equals 4 super Mills happily lies in between those curves. So it's not such a wild guess to apply these methods to get some qualitative insights for real quark-gluon plasma. As far as kinetics is concerned, we need to know values of transport coefficients, such as viscosities, diffusion constant, conductivities of various sorts. And of course, there are consistency conditions which must hold between them, so that is a useful check in gravity calculations. So there is a recipe at the moment, namely that in order to compute these transport properties from dual gravity, well, what we have to do, assuming validity of the gauge gravity duality, of course, the conjecture, all transport coefficients are completely determined by the lowest frequencies in quasi-normal spectra of a dual gravitational background. So if somebody gives you a gravity background for a particular gauge theory, in principle, of course in practice sometimes it's difficult, you have to use numerics and so on, but in principle, one can determine, there is a recipe how to determine all transport properties of this theory, all right? And this determines kinetics in the regime of thermal theory, where, of course, the dual gravity description is applicable. And alternatively, you can use things like computing, for example, thermal spectral function, which is essentially the imaginary part of the retarded correlators, and that can be computed from gravity, to determine also transport coefficients, and quasi-particle spectra, which is also sometimes quite interesting to do. So I'm happy to report that at this moment, all transport coefficients, first and second order, are computed, at least for one theory, in the regime of infinitely strong coupling, which is n equals 4 super-Young-Mills. So we have shear viscosity with all the results. Bulk viscosity is identically 0 because this is superconformal theory, but there is a lot of work, some of which was described by Steve Gupsara in the morning, but there is also very important work by Alex Buchel and collaborators, and perturbatively by Guy Moore, so this is not Greg Moore, and other people, for non-conformal theories in which bulk viscosity is different from 0. And then recently, Giuseppe Policastro computed the supercharged diffusion constant, so now this is a complete list of results for n equals 4 super-Young-Mills. So all these results show one thing. So you can look at, for example, electric conductivity in n equals 4 super-Young-Mills, and at weak coupling, so perturbative calculations show a very strong dependence on the coupling constant. You see lambda enters here in the denominator, and then there is this log and so on. So this coefficient shows a very strong dependence on coupling constant in the regime of weak coupling. When you go to strong coupling, you have a term which is independent of a coupling constant, plus some corrections. And this is a rather typical situation, even for non-conformal theories. So that one thing to keep in mind. So here is the standard plot by now of the shear viscosity in n equals 4 super-Young-Mills, of the shear viscosity of the entropy density as a function of a coupling. At small coupling, of course, this is a perturbative result which was known. For this particular theory, actually, it was computed quite recently, but qualitatively it was known since, I don't know, Landau-Lifshitz or even Maxwell, I suppose. And the contribution of string theory is this other end, where, of course, the infinitely coupling result is 1 over 4 pi, this universal result, but then there are corrections to it, and this correction was computed some time ago in 2004, but in fact, with a wrong numerical coefficient, which was happily fixed very recently, just several months ago by Buchel, and then there was an important paper by Myers, Paulus, and Sinha, where they considered the effects of the 5 form pieces in the effective action, supergravity action, and discovered that there is none. So on this result. So that appears to be a solid number by now in this particular theory as a correction in hot coupling. So what are second order? So there is also computation, full computation of the second order transport coefficients, which Shiraz actually mentioned already in his talk. But let me just qualitatively say at least a couple of words, what are these coefficients and why are they important. So hydrodynamics, of course, is an effective theory, and the fundamental degrees of freedom of this theory are densities of conserved charges. So in this primitive example, where you, not primitive, okay, it's a simple example of charge diffusion, you have a conservation law, and in hydrodynamic approximation, the fundamental degree of freedom here is the density of a charge, J naught. So we need to have a second equation which would express the current components, Ji, through J naught with some equation. So this is fixed law, of course, right? So it's a gradient of a charge which enters with a particular coefficient, which is the first order diffusion constant, which is specific for a particular theory. But there are other coefficients which are usually ignored. There are nonlinear terms here, and there are higher derivative terms. So when I talk about second order coefficients in super-Young-Mills, what I mean is the set of coefficients in front of these higher derivative terms, namely second order derivative terms. There are 5 of them, and all of them were happily computed from ADS CFT, and here they are. This actually, these values, numerical values, actually important for simulations of the experimental result at RHIC, as I will tell you in a second. So here is the plot. One thing that you can sort of infer from all these talks and why viscosity is important for experiments at RHIC and so on, is this plot of the fairly recent plot from Luzum and Romashke, which shows this coefficient of elliptic flow, which Steve Gubser describes in the morning in great detail. So the elliptic flow is a function of transverse momentum for various values of the ratio of the shear viscosity to the entropy density. You can ignore everything on this plot except for the white dots. So these white dots are experimental results from the real elliptic flow observed at RHIC. This is QCD results. What you can do, you can solve the equations, Navier-Stokes equations, with various coefficients, transport coefficients, and other things like initial conditions as an input parameters, and try to vary these input parameters to see if you can match the curve. Okay. There are more parameters than just A/S, but the good news is almost all of them, except for a very few, are completely irrelevant. I mean, you can vary them as essentially as you like in a reasonable range, and they do not really strongly affect the matching of the experimental results. So you can see here, with a particular set of initial conditions, which are known as a color glass condensate, you can have these blue squares, right, which corresponds to A/S equal to 0.16, more or less well approximating the experimental data. But then you can say, what about other parameters which I have? I can dial some other parameter, and of course it will go away. And indeed, this is so for only one of these parameters, which is mostly severely affecting these results, and these are initial conditions with initial nuclear density profile. So this is for color glass condensate. Now remember the blue squares. Now you can look at the same plot with the different initial conditions, which are known as the Glauber initial conditions. And here you have these blue dots now below experimental line, and you may wonder that maybe A/S equal to 0.08 is a better approximation. So there is a certain range which is not fixed. We don't know how to fix it. However, this range is not infinite. So we can constrain the value of A/S by comparing with, for QCD, by comparing these data with various numerical simulations. So what is the current situation in QCD? So first of all, there is this universality result, right? So theories of gravity duals in the regime where the dual gravity description is valid must have A/S equal to 1/4 pi, which is 0.08. So that was the old result. There are 3 proofs of it, more or less independent proofs, which I will not go into, but that is more or less well known by now. Now, RHIC elliptic flow from matching with this data that I was showing constrained A/S by being somewhere from 0 to 0.2. In direct lattice QCD simulations by Harvey Meyer, in the temperature range which correspond to RHIC, give you A/S somewhere between 0.08 and 0.16. And then there are other, so you can compare these numbers with what is known for other liquids in nature, for other systems in nature. Notice that, so you can compare it, for example, with trapped strongly correlated cold atoms like lithium and calcium. And these guys behave hydrodynamically, and they're also a strongly coupled system with A/S at the minimum given by 0.5. This can be compared with results for liquid helium-3, for example, which gives at the minimum A/S approximately 0.7. So philosophical sort of outcome of this comparison is that at the moment it seems that QCD provides us with the liquid or the state of matter which has the lowest ratio of A/S in nature. All right, so now that part of the talk is completed. We have to now lower the temperature completely and consider systems at finite density and either low temperature or 0 temperature. So this part of the talk is based on this recent paper written with Andreas Karch and Demson. So what we would like to do is the following. We would like to understand if the holography gives us a tool to understand the behavior of quantum liquids. And for quantum liquids, of course, there is a certain classification, very well known. So quantum liquids in P+1 dimensions typically can be classified just in basically two large pieces. One is quantum Basel liquid, in which the low energy elementary excitations are given by phonons, and specific heat accordingly at low temperature will behave as temperature to power p, where p is the number of spatial dimensions. So this is t cube in our normal space. On the other hand, fermions, almost universally, would behave as the quantum Fermi liquid, which is described by the Landau Fermi liquid theory, in which fermionic quasiparticles form the low energy elementary excitations. But in addition to that, there is also a bosonic branch, which is known as the zero sound, and a specific heat at low temperature, universally independent of the dimension, will scale as temperature. So these results of Fermi liquid theory, of course, is due to Landau, whose 100th anniversary we celebrate this year. And so he proposed the Fermi liquid theory and also found this zero sound mode, which was later discovered in liquid helium-3 as an experimental verification of the Fermi liquid theory. Curiously enough, Landau died in the year when string theory was born. I'm not sure what significance you can attach to that statement, but it's curious to note. So there are also substances which show departure from normal Fermi liquid behavior, and this usually occurs in 3+1 or 2+1 dimensional systems with strongly correlated electrons, or in 1+1 dimensional system for any strength of interaction, which is known as the Lüttinger liquid. So one can apply holography to study strongly coupled Fermi systems at low temperature and see if the Landau Fermi liquid theory features are reproduced in the strongly regime of strong coupling. So the natural and simplest candidate for such an exercise is the theory with known holographic description, which is just n equals 4 super-Yang-Mills coupled to nf n equals 2 fundamental hypermultiplets of mass m. At finite temperature and non-zero chemical potential, which is associated with the baryon number density in the of the charge, which is a U1 charge of the UNF. UNF is the global symmetry of this theory. So basically, we can call it a baryon charge. Of course, it's just not just baryons, right? There are also scalars because the theory is supersymmetric. But it's the closest approximation to the Fermi, to fundamental fermions that we have with a good known holographic description. So there are two dimensionless parameters, right? In n equals 4 super-Yang-Mills itself, there is one, at finite temperature, there is one dimension full parameter, which is the temperature itself, and there is nothing else. Here we have more degrees of freedom because we can play with the density over temperature, dimensionless parameter 1, and the mass of these hypermultiplets over temperature gives us a second dimensionless parameter. Well, so the holographic dual description of this theory in the limit of infinite n and infinite Hopf coupling, but nf being finite, is given by the d3-d7 system, with d3 branes replaced by the ADS-Schwarzschild geometry, and d7 branes embedded in this as probes. So the fact that this is a probe brane approximation is reflected in the statement that nf is finite and ratio nf to nc is extremely small. So that was a construction which was first put forward by Karch and Katz in 2002, and many people worked on it ever since. What we would like to do here is, so this is a bit of geometry, right? So this is a black brane, ADS-Schwarzschild black brane. A finite temperature is given by the presence of the horizon here with radius RH. The dynamics of D7 branes is described by the dBi action, and the word volume U1 field A mu couples to the flavor current J mu at the boundary. So if you want to have a theory with non-zero chemical potential corresponding to baryons, we would like to have non-trivial expectation value of this flavor current J node, component J node, and therefore we need a non-trivial background value of a node in the bulk. So the background is given by the metric plus the non-trivial value of the field of the component A node. We would like to compute two things. One of them is the specific heat at very low temperature, and by low temperature I mean the temperature much less than the appropriate root of the charge density. And we also need to check for the zero sound. Landau predicted that it should be the case. So we have to check for zero sound. The simplest way to do this is to compute the charge density correlator, the retarded correlator of J0, components of the flavor current, and see what kind of poles this correlator has. That will give us a quasi-particle picture of the theory. And if zero sound is there, it should be visible as a pole of this correlator, even at zero temperature. So in Fermi liquid theory, zero sound can be thought of as oscillations of the Fermi surface. It's not the ordinary sound, which only has sense, I mean, as a sound wave, is a deviation of pressure and energy density from equilibrium at non-zero temperature. So here we expect this thing to have a pole even when the temperature is exactly zero. So let's check holographically if our expectations are correct. So first of all, we compute specific heat, and in p+1 dimensions, so ignore all these prefactors, focus on this dependence of specific heat on temperature at very low temperature. The dependence on temperature is non-trivial. It's not the expected Fermi behavior, which is linear in T in all dimensions, and it's not the Bose behavior, which would be T to the P. It's T to the 2P divided by the density of the charge. Now, so that is a bit unexpected. However, if you compute the retarded charge density correlator, we happily find the zero mode propagating mode, which we can identify with zero sound, because even at zero temperature, so there is a pole in this correlator, with the dispersion relation, which is written here, there is a speed of the zero sound, which in this approximation of infinite coupling simply coincides with the speed of the normal sound. It's 1 over square root of p, 1 over square root of 3 for 3 dimensions. There is also non-zero attenuation, which is proportional to q squared, q being the spatial momentum, and then there is a density in the appropriate power. So this mode, this propagating mode, it's not a hydrodynamic mode. This mode is not a superfluid phonon whose attenuation would scale as q to the p+1. So this is really something that can be identified with the zero sound, but the specific heat is different. So you can check other features of this theory and ask a question, the answer to which at the moment we don't really know completely, but you can ask a question whether or not holography identifies for you a new type of quantum liquid, which is different from Lüttinger, different from Fermi liquid theory of Landau, and different from Bose one, right? So, because it's a non-trivial question to ask, what is the full set of classes of quantum liquids at small temperature and finite density? All right, so let me come to the conclusions. So the program of computing first and second order transport coefficients in n equals 4 apparent Mills at strong coupling at large number of colors is essentially complete. These calculations are helpful in numerical simulations of non-equilibrium QCD, and they also stimulated developments in other fields, such as lattice QCD, perturbative QCD, and condensed matter. So that is also something to remember. We need, of course, a better understanding of phenomena like thermalization and isotropization and the full time evolution of the fireball of this quark-gluon plasma done as rigorously as possible. So that is a big challenge because that involves a lot of very precise numerical work, some of which was started by young collaborators. We also need a better understanding of corrections from high derivative terms. So already these papers were mentioned today in the talks, but that would be good to develop even more. And of course, the Alice detector at LHC will provide more data at higher temperature. So high temperature means that the theory will be in some sense closer to the conformal one, temperature being higher than at RHIC. At the same time, it will be closer to the perturbative region. So the community of people who for years doing perturbative calculations, of course, hope that in fact the results from Alice will be described very well by perturbative calculations in thermal QCD, and we will have to see if that is really the case, that there is some drama here, potentially. So at low temperature and finite density, one question which I already asked is, does the holography identify a new type of quantum liquid? I think that question would be interesting to answer. And in particular, to answer such a question, we would like really to start studies of perturbative regime of supersymmetric models at finite temperature and density, because that would be very helpful to understand. We know holographically what is happening, and what is happening is a bit enigmatic and a bit unexpected. We don't really know what is happening in the same type of models perturbatively, so that would be probably the next step in this direction. Thank you very much.
Questions? Yes.
What do you mean by G-unit is the case with the D7 brain? Because if you have hypermultiplet, it automatically brings the coupling constant to weak coupling in the infrared, right? So how do you take the holographic dual if it's weakly coupled in the infrared?
Well, that's, I mean, by holographic dual, all I mean is the D3, D7 construction, right, about...
So you are not saying that system is dual to the theory with n equals 4 supermills coupled to n equals 2 hypermultiplet, because it should get just weakly coupled theory, right? So
yes.
It should
yes.
be something different.
That's right. So yeah, one can see what is happening at the other ends of the. I mean, if you just have a Lagrangian, you know, there's a number of flavors.
So let's thank Andrei again.